Well, good morning. Thanks for coming out today. And my name is Brian Costello. I'm from TE Connectivity, and today I'm going to talk about a really exciting new technology that TE is developing to increase the capacity of bus bars by making use of liquid cooling. First, I want to start with why we launched into this effort. You know, with the IT equipment power levels increasing greatly, obviously the power system has to adjust accordingly. And then the way the systems or the bus bars are really rated for a temperature rise. And so we try to keep them below a certain temperature specification. And in a traditional system with airflow, we can take advantage of the airflow from the rest of the IT equipment in the bus bar. But for low flow air, where we're actually using, cold plate cooling, it's a little more difficult because you're losing a little bit of that airflow. And so we are using the liquid infrastructure then to pump into the bus bar. And in that case, we then have the ability to cool it, keep it lower, increase the current capacity. So we started brainstorming the different ideas, and the first one we came up with makes use of a tube that we insert into the bus bar itself. Now in this case, we're showing on the left side the assembled bus bar, and then we create slots in the rear section of the bus bar, and that's where we have a wider section behind the mating interface. And then we have our coolant inlets that in the case of using a tube, we can actually put them anywhere in and actually greatly, or even put more liquid through smaller cross sections. This is a standard ORv3 48 volt bus bar, and we can see with the laminated section in the exploded view. Now, instead of just being a solid copper part on either side, in this case it's a full assembly where we insert those tubes. A little more detail about the cross section. So you can see we're using a rectangular tube to try to keep it in the same form factor as the bus bar itself. Then we bond those tubes in with a thermal epoxy to minimize the amount of thermal resistance between the conductor itself and the coolant tube. And then we have a support bracket that mounts around the bus bar itself, and then it subsequently allows it to be mounted to the cage. And then we have either top and bottom at various locations, we have our coolant fitting locations. Now on the far right, what we're showing is a two-zone system. In this case, if we had a power shelf, let's say in the center of the bus bar, we have our cold coolant coming in at that location. That's going to be the hot spot of the bus bar. So in that case, we're going to get better efficiency by putting the cold fluid there. Conversely, if you had a power shelf at the top and bottom, you would reverse that and you put the coolant in those zones. Or again, you can just do a typical single zone type system. A little more detail about the tubes themselves. So in this design, we made use of an aluminum extruded tube that goes along the main body of it. And then we have die-cast aluminum end caps that we bond onto the ends, either welded or epoxied. And then finally, we have to electrically insulate the tube itself. Obviously, it's touching into a 48 volt bus bar, so we have to make sure if we have liquid that is electrically conductive, we can't touch it to the bus bar itself. So we apply a coating to the outside of the tube to electrically insulate it. The next design that we looked at makes use of integral cooling channels right into the bus bar itself. And in that case, we're using an extruded copper bus bar, and then we just form that feature during the extrusion process. The rest of the construction is somewhat similar as far as we have the support brackets that mount on either side of the coolant tube zone, and then we can subsequently mount that onto the bus bar cage itself. The challenge with this design is then we have to coat the inside of that full tube and make sure that there are no voids, there's no ability for the coolant to actually touch the copper. So that's a little bit of a challenge that we're working through right now. The attachment of the fittings go on the outside. In this case, we're showing it on the top and bottom. We're also evaluating other methods where we're actually just going to seal off the ends and then apply them to the sides, similar to what we showed with our tube-based design. So once we came up with a few designs like this, the next step was to really look at what the performance would be thermally. So we designed, or we just did a simplified geometry bus bar design. This is a full-length design where we're applying the power to the center of the bus bar. Then we're tapping off the power at multiple locations along the top and bottom. So this would be similar to what would happen if in a typical rack with a power shelf in the center. The simulation result here, we're showing the thermal profile. So we had our coolant coming in on the lower right side and the exiting on the upper left. So we're see that's obviously the cold spot. We have cool fluid coming in, and there's a very low current density in that zone. As we get to the center, we see the hot spots. The hot spot coming from the power shelf entry, and then that thermal energy is then moving, with the fluid flow. And we're showing it here with the two different designs. The upper one is the tube-based design, and the lower one is the hollow bus bar design. And we see that with the hollow bus bar design, since we don't have an epoxy bond in that zone, it's got a better thermal connection, so it performs. It has almost half or a little more than half of the thermal or the T-rise. So it is performing better per our simulation. And then we ran actually kind of a factorial analysis. So we had our two different designs. We had two different coolants we evaluated. We also evaluated no coolant. So this would just simulate the bus bar just as a standard it is today, with just air kind of cooling. And we also used two different boundary conditions in our analysis. The first of which, where we applied 1200 amps to the bus bar and then measured the T-rise in the bus bar. The second design or analysis below was where we varied the current to really just drive it to a 30° C T-rise. And again, we have two different fluids. With the baseline design being air, we had a 30° C T-rise, which is what we really set, is where we really set the 1200 amps to. And then we see that the T-rise differences. So we had 12 or so degree C T-rise with the tube-based design, and then we had 6.5 or so degree T-rise with the hollow. So we really see a benefit of that hollow bus bar design. Another thing to note on this is that we actually reduced the cross-section of the bus bar. So you can see in the center picture, it looks kind of like a zigzag, and it was actually, you could see it previously in the upper picture where we had two voids. We actually removed copper because we felt we really didn't need as much when we were having that cooling. So we're actually using a more efficient use of materials. It's also easier to extrude that shape because we don't have the thick and thin sections. And the summary of the analysis really, again, I think really says it all, where we really see a huge increase where the baseline off to the left side is the air, and then as we get to a 30° C T-rise, and the efficiency increases, we really see a huge benefit to the liquid-cooled bus bar. So the next thing we set out to do after we had our analysis was to go build one and see how this would all work. So I originally wanted to really build a full-size bus bar that would go into a standard rack. However, we were limited by the prototyping capabilities we could do. Really forming the tube. We weren't going to go and get an extrusion tool made, so we had to form it and weld. So it was a little bit different in the manufacturing method, but we were limited to about 1 meter, and so that's what we ended up designing, this test bus bar. And also we're putting the current in the one side, we're jumping it across on the other, and then we're bringing it out the other side. So after we had a design, we went back and just re-simulated because we really couldn't rely on the same simulation results, and so in this, we had a current. We used actually 1,000 amps, and the reason we reduced that a little bit was because in our lab we had a limit on that particular power supply to 1,000 amps. And the other thing is we changed it where we're using 100% water, and the reason for that was in our lab we didn't really have a recycling system for either an FC40 type fluorinated material or even an ethylene glycol, so we just switched to water so that we could just get the data and see how that would work. And so then we went out and built bus bar. So here's a couple of pictures of the bus bar that we made for the test. And then this is our test setup. So we had our power source shown on the left. We have our bus bar assembly on the table, and then the temperature recorder and the fluid behind it. We set the temperature to 30 degrees C for the inlet fluid. That becomes a little more important when I talk about once we get our results. But that's a little lower than we typically think we see in the typical deployments. But we used that. It was a little it worked good for us. And so when we look at our test results, we measured the temperature at 6 locations, 3 on each side of the bus bar itself. We also measured the inlets and outlets as well. And so in this case, again, we ran 1,000 amps. We let it dwell for 90 minutes to make sure that we were at total equilibrium. We weren't going to see any further T-rise. And again, we're using the water as the fluid going through it. Now, the total temperature is accurate as far as for the 0.15 liter per minute, which was the flow rate. We did 2 flow rates, the other being 0.3. We saw, it was 47.5 degrees C total, and then also for the 0.15 and for the 0.3, it was 40.5 or so. Now the T-rise, our lab used our traditional methods when we do our bus bar testing. So when they calculated T-rise, they calculated it to the air temperature, which, as I was arguing with them, that really wouldn't be accurate for this particular test, simply because with 0 current running through the bus bar temperature is going to be 30 degrees C because of the coolant temperature. So there was a 4 degrees C shift. And so I didn't want to adjust the data that came from our lab, so I left that alone, just wanted to explain that. But so we can really see is that we have about a 17.5 degree T-rise for the 0.15 liter per minute, and we had about a 10.5 degree C T-rise for the 0.3. So this data correlated pretty well with our simulation results. And so we were very happy, with these results. We're really excited that this technology, about the technology, and that we have, a great way to increase the current capacity of bus bars. It significantly increased the ability of the bus bar to carry current because we're keeping it cooler. We found that the hollow bus bar design obviously has a much better thermal efficiency, and so we get even better results with that. We do have some challenges with manufacturing on that, so we're still working through some issues with that. We also found that the ethylene glycol worked much better than the FC40, or moderately better. And so, our next steps are to do some prototyping on the hollow bus bar design, and then we're going to validate those thermal results. And then beyond that, and kind of our call to action is really to get in sync with system providers that we can work with to implement this into an actual rack environment. And so we're going to be reaching out to some different companies to partner with us on that. And if anyone would like to partner with us, we'd very much like to hear. Please come to our booth and talk with us, because we think that in an actual deployment, then we're going to get the real situation, the real amount of current flowing, and we'll get we'll really be able to validate in an actual real world locate or evaluation. So lastly, if you want to see more information about this, we have the bus bar at our booth in the outside Expo Center. And then we also have a lot of information about our power connectors, our power cable assemblies. We have our product management team here that can answer any question you have. We also have some displays of other signal connectors that are related to OCP. If you'd like, get more information about the cooling environments, please come to the wiki for the cooling environments or the rack and power page. With that, any questions? Yeah.
Yeah, based on your simulation data, you prototyped with the formed bonded bus bar?
Yeah. Well, the bus bar itself was a machined bus bar, but the tube was formed.
Oh, I thought your bus bar assembly, when you had the embedded fluid channel, was a formed bonded assembly.
No, yeah, the bus bar was just, it was a solid chunk of material that we machined out.
Okay, then my question's non-valid. Then I was going to ask about the performance difference between the formed bonded assembly and the.
But it's an interesting point you make, because one of the things that we can do with this that we're really interested in doing is actually possibly forming the copper,
Right.
to get away from that ability. And if we can do a roll form, because we have such good thermal efficiency that where we're cooling it with the tube, and the fluid going through, we may enable that, which would make a lower cost, way to make
get away
the
from
bus bar.
extruded copper. Yeah, exactly.
To get away from it, right. We haven't gotten that far yet, but that's one of the ideas. Once the engineering team gave me the drawings of it, so we could possibly form this shape. We don't necessarily need to do an extruded shape.
Oh yeah, I thought you tested with that, so that's my.
No, it was just it was a prototype, so we just machined it. And if you see the prototype that's out on the floor, it was really developed just for this test. It's not designed to be mated to a connector. It was really just for this evaluation.
Exactly. Cool. Thanks.
Sure.
I saw that you had tested for 1000 amperes. It means that with 48 volts, it's approximately 48 kilowatts per rack, right?
Again, this was just for this test, but yeah.
Yes, I mean, do you see the potential limits per rack with on-chip cooling? From the power delivery point of view.
A limitation from the bus bar?
Yes. I mean, how much kilowatt we can deliver with the liquid cooling bus bar for OCP rack?
So we're seeing probably from our testing somewhere between about a 3x improvement or ability to deliver power from the bus bar itself. Now, there's a lot more to the whole ecosystem as far as the interconnects going in, the power shelves, with a multi-power shelf, rack. One of the other benefits of the tube-based design is we could actually create thermal zones. And so we could really increase each zone by 2 to 3x, and you can have multiple zones. We see ability to greatly increase. I don't have data to say what it exactly would be, but we definitely see a current carrying capacity can go up threefold. And that was actually with that formed shape with the hollow. That's really a hollow bus bar design actually. They can get to a 3x. We can greatly improve that efficiency and the carrying capacity, but we don't have data to say what it would actually be calculated out. And that's one of the reasons we want to get to do a full deployment in a full size rack, that we can really get some better test data on that type of a environment.
Thank you.
Okay, thanks for coming today.